Hello everybody, my name is Utkrist and today I'm going to be presenting on adversarial sparse transformers for time series forecasting. This paper was originally written by Wu and team from Tsinghua University and Tencent AI Labs. Time series forecasting can be very useful across many different domains. For example, in business, if you're able to accurately predict business demand over a certain period of time in the future, you can better optimize your business operations in order to boost efficiency. In finance, if you're able to, say for example, predict the prices of a certain asset over a period of time, you're better able to manage risk for your clients. So time series forecasting can be very useful not only in business and finance. These are just two examples. They can be useful across many different domains, right? So this is why time series forecasting is an important problem today. Now, a lot of forecasting models use autoregressive methods, and most of them are also point prediction mechanisms. So let's go over what autoregressive methods are and what exactly is a point prediction mechanism, right? So autoregressive methods are generally methods that use information from the previous time steps in order to make the prediction for the next time step. For example, what RNNs do, right? So they take information from the previous time steps in order to generate the new time step, and then when they have to generate the time step after the current time step, they will use the prediction made in the current time step as well as the predictions from the previous time steps in order to generate that next time step, and on it goes, right? So that is what an autoregressive method is. Now, what is a point prediction mechanism? Point prediction mechanism basically means you're predicting the data point for a certain time step, one time step at a time. For a certain sequence, one time step at a time. So that's what RNNs basically do. The problem with this mechanism is that if you're generating a prediction for a certain time step, and if there's a certain level of error in that prediction, you'll be using that prediction in order to generate future time steps as well, which ends up accumulating error as you move along the time steps and the time series diverges from the original time series. So this is called the error accumulation problem. And in order to get around the error accumulation problem, the authors of this paper introduce a generative approach rather than a autoregressive approach to time series. The idea here basically is if we're not generating predictions one time step at a time, then perhaps we could get around the error accumulation problem. So in order to do this, in order to avoid having to generate point predictions, the authors suggest a generative adversarial network with a sparse transformer as its generator. So generative adversarial networks, for those who are not familiar with GANs, they have two major components within them, a generator and a discriminator. A generator is responsible for generating a distribution, and the discriminator is responsible for taking an input distribution and telling whether or not this particular input distribution was generated, or if it's an original distribution from an original dataset. So in this particular architecture, the generator is going to be the sparse transformer, which is able to generate a time series for a certain number of time steps. And then the discriminator is a simple feed-forward dense neural network that can do binary classification. So the discriminator takes in the output from the generator, so the output time series generated by the sparse transformer, then it will tell whether or not this particular time series was generated or if it's the ground truth. So that's the high-level architecture of the implementation of the adversarial sparse transformer in this paper. And within the encoder, within the generator, there is an encoder and a decoder component within the transformer, as well as the encoders and decoder components themselves having various layers of operations. So if we start off with the encoder, there's a self-attention layer, and then there's an addition and normalization for the attention weights, which is then fed through a feed-forward neural network, whose output is then added and normalized again, right? So the decoder takes in the original ground truth, right? So it takes in an original time series sequence for a certain number of time steps. And while it's not explicitly mentioned over here, it uses a masking mechanism in order to hide the future time steps so that learning actually happens, right? So you can see various layers of operations similar to those in the encoder, stacked against one another. And in the second self-attention layer, the decoder takes in the output from the encoder in order to facilitate learning. So this is the high-level architecture. And the results are as follows. So the evaluation metric used here is the quantile loss, and a quantile loss basically measures the similarity of two distributions, right? So the lower the number, the better the performance. The authors report a 0.042 and 0.025, but my results from my implementation resulted in a 0.975 and 1.015, which is significantly higher than the author's results. Now, there could be various reasons for this. I did not have enough time to tune the hyperparameters in this model. And furthermore, the number of epochs for training was only 20. In hindsight, if the number of epochs was more than 100, then there could have been substantial performance, but we can run this experiment again for longer epochs and different parameters in order to see whether or not the results in this paper is reproducible. Thank you very much.